Greetings, rock stars, ninjas, ninjets, Jedis. We are here for Jedi Lesson 4, going into Part 2 of Ethernet, focusing on the data link layer. So if you recall from our previous message, sorry, the cocaine hasn't kicked in yet, kids. If you remember from our previous video on the OSI model, we had looked at the physical layer, things concerning wires or voltage standards, cabling standards, whatnot. Now we're actually going to look at where those physical forms of medium start to take on a value or an intelligence, and that is layer 2, the data link. So, reminding you, the OSI model is really a framework that is set out to discuss those different functions and how they interoperate with each other, and how to break down, your entire experience as a user into basically a standard set of functions based on what you're doing. Are you trying to initiate a session remotely? Are you trying to route traffic or whatnot? So the data link layer itself is layer 2 on this model, and it's concerned with the local delivery of frames between devices that are on the same medium. So basically wireless to wireless, Ethernet to Ethernet, so on and so forth. When you start crossing other mediums, you do what's known as bridging. So layer 2 is focused keeping that traffic on the same type. So the layer 2 protocols tend to focus on, the reliable transmit across that physical medium. So it has to check for transmission errors. It has to package those bits into frames. It has to manage some sort of addressing scheme, and it has to control access to that physical medium from all of the devices that are trying to communicate. So let's scroll down here. The essential core functions from a bird's eye view of the data link layer is, first of all, physical addressing, which is going to form those zeros and ones into something meaningful. And the two types of forms that it's going to take would be first of all, the headers, which are going to, above all else, give the destination and source address, but are basically going to say what to do with this packet, how you treat it, how do you get it from point A to point B. And then the second part would be the payload, and the payload is what contains the actual data. If you're downloading an MP3 file, that is in the payload section. So two basic parts of the frames that start to be formed with these zeros and ones, whatever the transmission medium be. Error detection, again, physical mediums are imperfect. Especially if you consider wireless, how easy is it to have interruption in a signal that's broadcasting RF signals over the open air? So there has to be a way to detect for errors in the frame. Access arbitration, basically you have all of these devices contending for access to the same media. Think about it this way. You're a pimp. You have all of your hookers coming up to you and screaming at you at once. One of them wants her crack. One of them wants you to go into the room and beat some guy up who didn't give her money. One of them wants her money. So how do you deal with all of these? How do you proxy 20 hookers yelling at you at the same time? Well, it's kind of the same thing in networking. You have a cell phone calling a cell tower, making a phone call, and then suddenly your mom picks up her cell phone, makes a call, your colleagues at work. There has to be a way to arbitrate, to manage all of this simultaneous access to the physical medium, and that's what access arbitration addresses. And then the last one, of course, is to identify the upper layer protocols. This might surprise you, but there's dozens and dozens and dozens of protocols, quite more than we're going to explore here. You have to tell all these devices, hey, what data am I sending you, so it knows where to send this traffic. One other thing, I want to just kind of briefly go over some of the devices and technologies. You're probably familiar with a lot of these. So layer 2 devices, bridges, switches, wireless access points, network interface cards. These are things that take these communications that are in their physical medium, again, be it electrical signals from Ethernet, be it a fiber connection, which would be beams of light, an infrared signal, an RF signal from wireless, and starts packaging it into meaningful frames and payload. The protocols, oh, look at that. I have email coming in. It's work. I'm just going to ignore it. I've worked enough today. Even Jedis need a break, kids. So the protocols, the main one, of course, is that we're going to look at is Ethernet, but also wireless as well. That's another very common LAN protocol. And by LAN, I mean all of the physical medium is going to be local to your location or your site. ISP protocols, on the other hand, you're still going over a medium that is not owned by you or your corporation, that is not private but rather public. So PPP, which stands for point-to-point protocol. If you remember the old days of America Online and dial-up modems, you'd click a button to connect, you'd get that lovely connection sound in the background, and then finally you were able to connect. That PPP is actually the protocol that was being used in the background. It was essentially initiating a phone call. So it's starting up that connection, getting you connected to your service provider's point of presence, and now once the connection is established, you can send traffic across. The difference between Ethernet off the bat and PPP is that PPP is an on-demand communication. Ethernet is always on. There's no off and on. It is just set up, ready to communicate. PPP must establish a session first. So it can drop connections. Those connections can time out. PPTP, L2TP, those are kind of tunneling versions. They are still based on PPP frameworks. They just evolved in different directions. Frame relay, ISDN, or specifically the layer 2 part of ISDN is Q.921. T1 connections, ESF, or extended superframes. So those are some of the ISP layer 2 protocols. If you want to read more about them, Google. We'll probably be touching on a couple of them in later videos, specifically PPP and T1, since they're so common in the service provider area. I suspect I'll be doing a video on those later on. So, DataLink. The framework is this. I just want to kind of touch on this before I start doing the deep dive. When you're thinking about this, it's composed of two sublayers, and basically the two sublayers are what is handled in hardware, what is handled in software. The LLC, or logical layer control, that is controlled in software. That's going to do things like flow control of your traffic or regulating the rate. It's going to handle error detection and identification of the layer 3 protocol, as well as encapsulation and decapsulation. And just so you understand, encapsulation, decapsulation, that's the actual process of taking those zeros and ones, whatever their form, again, RF signals or copper transmitting voltages. Encapsulating, decapsulating is the process of taking that information and making it intelligible, adding the frames, the header frames, and adding the payload, or rather I should say interpreting it, encapsulating, decapsulating. Media access control, or MAC, that is what's done as hardware. The primary function of this is going to be hardware addressing, also media contention, or as we saw above, communication arbitration. So those two are actually handled by the hardware. So kind of going through, now we're going to start really digging in deep to those four core functions. So let's start with addressing. Before we touch too deep on it, what I want to say is there is a difference between physical addressing and logical addressing. When we're talking about layer 2, we're talking about physical addressing. When we're talking about routing traffic of the internet, that's logical addressing. And here's the best way to really think about this. All right? Logical addressing is where you are. You are driving in your car. You're, in the back room doing cocaine off a hooker's breasts. Where are you? Who you are is your physical address, your name tag. Hooker 1 is Bambi. Hooker 2 is Candy. Who you are does not change. That is your physical address. That is what we are addressing here. Your logical address can change. You can be on a flight to Miami. You can be driving in your car to Chicago or Arizona. Your logical address is where you are. Your physical address is who you are. And all layer 2 protocols have a way of dealing with this. There's different mediums. All the protocols we showed you, PPP, frame relay, T1, they all have a different way of doing this. We're going to focus on Ethernet to help you better understand that. So Ethernet's physical addressing is called a MAC address. Surprise, surprise from above, media access control. And it is basically broken down into 48 bits. Now, the way it's represented can seem a little tricky to the uninitiated. It is not stored in binary, so zeros and ones, and it is not stored in typical decimal notation. It is stored in something that is called hexadecimal. So with decimal, you have each columns being representative of tens, hundreds, thousands. It's multiples of 10. Hexadecimal is multiple of 16. So this would be the ones column, this would be the 16s columns, this would be 256 column, and so on and so forth. So you don't really have to get too deep into this. Your Windows Calculator can do this for you, and I want to show you how to do this. Do I have you here? Yes, I do. So if you, first of all, you go here and you make sure that you're on Programmer, you'll get that option. So first let's check decimal, and let's pick a simple value. Let's pick something lower than 16 first. If you select 8 and you go to hexadecimal, your value is going to be the same because your ones column is still there. Let's pick a value here, 14. Go to hexadecimal E. Just to point this out, rather than going from 0 to 9, it actually goes from 0 to 9, then A, B, C, D, E, F, F being the value 15, and once you get to 16, then you start going to the next column, which would be a 1 in this case. You don't really have to know this. I just want to show you have the ability here to interpret hexadecimals. You can certainly Google more. Just to give you an idea, 249. What would that be in hex? F9. 255, what would that be? That's going to be FF actually. I have to clear that out. Go to decimal, 255. It's probably going to be FF, and indeed it is. All right. So the notation of this is typically there's going to be two types. There's Cisco notation and then industry standard notation. And as you can see, how many of these you group up. Each one of these guys right here, so you can see, represents 8 bits out of those 48, so you're going to have a total of 6. It depends. Standard notation is going to have a colon between each grouping of 8 bits. With Cisco, they actually group 2 pairs of 8 bits together and put a period instead of a colon. You know, half of one, 6 dozen of the other, whatever. What is important, however, in the structure of the address is that the first 24 bits are called the OUI, or the Organizationally Unique Identifier. The last 24 bits are the Interface ID. The OUI is going to be specific to a manufacturer. Intel is going to have their own OUI, or sets of OUIs. Cisco is going to have their own OUI. You can actually look this up. We kind of go to a command prompt here. I will bring this down so you can see what I'm doing. Let's just do an ipconfig/all, if I can type. Alright, so let's look here at my Ethernet adapter. This physical address is my MAC address. So if I want to see who my OUI manufacturer is, I can copy that here, minimize that. Let's go here. Going to have to do an OUI search. Sorry, I have to kind of bring this down here. Alright, let's see what we got. I think this one will do it for us. I believe it will. Sorry, bear with me. I'm trying to cram this all in a very small space here. Here we go. So we search this. OUI, search. And what do we know? Dell. As it turns out, this is a Dell laptop. So kind of a, you know, a unique troubleshooting tool. It can also be a security device too, and very, you know, legacy type implementations. You could say, hey, all of our laptops are Dell. If we need to filter by a MAC address, we could say it must be a Dell OUI. You can go and search out all of Dell's values. Not necessarily something I'd recommend in today's time, but it was something that was used in, say, 1997, when you had very limited options for a Radius server. So that's just the basic structure of their addressing. Again, first 24 bits identify the manufacturer. The last ones are unique, specific to the interface. So what you really have is 16 manufacturer IDs, each one with 16 million values. As you can imagine, I'm sure at this point Dell has produced more than 16 million laptops, so they probably have multiple OUIs. Alright, going down, that's physical addressing. Now let's look at error detection. Sorry, I scrolled up too fast. Error detection, I want to point out first of all, as you can see here, is not error recovery. It simply identifies an error. The way it's handled in Ethernet is it has a 4-byte trailer on the end of a packet that calculates the value, stamps it, sends it out. When the destination receives the packet from the sender, it calculates that value itself and then compares the value that was stamped by the source when it sent it. And if those two values are different, there's an error. Typically, Ethernet will just drop the frame and rely on the upper layer protocols to resend that data. Not all layer 2 protocols behave that way. Some actually have the error recovery mechanisms built in. Ethernet, however, is not one of them. If it detects a bad frame, it essentially drops it and waits for a retransmit from the upper layer protocols. So again, just so you understand, I am the source. I have my packet. I'm sending it out to the destination. I calculate this frame check sequence value. I stamp it here in this FCS DataLink trailer, send it out to my destination. The destination runs its own calculation check and compares it to the value that the source put in the FCS and sees if they're the same or they're different. If they're the same, the packet is good. If the packet is different, then it's an error packet and it drops it. The next function, of course, is the identification of the layer 3 protocol. It basically has a value there. Every single protocol has its own unique value in the DataLink headers, and that is how it identifies. If you're 255 or if you're 312, whatever your value is, it's going to say, hey, I'm IP or I'm AppleTalk, whatever the case happens to be. That is how it's going to identify where to send it to, who handles this traffic. Last one is arbitration. And arbitration, as I said before, it can seem a little bit daunting. It's a little bit more of a complex mechanism. First of all, the technology that handles arbitration is CSMA CD, Carrier Sense Multiple Access Collision Detection. I think really the collision detection is the important part here. Again, from my earlier point on this video, access arbitration is dealing with multiple talkers on a network wanting to communicate at the same time. You have to contend with all of these simultaneous requests in a way that won't destroy the network. Well, with Ethernet, it basically allows everyone to talk at the same time. So when they were looking at this, they said, we have to find a way to deal with this. If you have a collision, which would be 2 or more packets transmitting at the exact same time, well, you're going to have a problem, and you're going to really turn all of the multiple sender source into garbage. It's going to be unintelligible when you have a collision of 2 or more packets. So the way they deal with this is that each endpoint has a random timer that they set before transmitting. Now, once they start transmitting, the more usage there is, the more bandwidth, the more you're going to have the likelihood of a collision. Typically, when you exceed 40% of bandwidth utilization, you're going to start getting significant and even exponential increases in your likelihood of a collision. So what happens if a collision occurs? The first thing that happens is a collision is detected. Now, let me stop for a second and say, how is a collision detected? Well, number one is you get a ton of FCS, frame check sequence errors on the line. Another one is you're not going to be within typical communication standards. For instance, with Ethernet, you're basically transmitting voltages. Those voltages are going to be far outside the normal range. If you remember the layer 1 standards for Manchester encoding or 4B, 5B, those define specific voltage standards. When you have a collision, it's going to far exceed those. You're going to get garbage data, so it's going to recognize you don't have an intelligible packet here and say, aha, a collision is detected, a collision has occurred. So the first thing it does once it does detect that is it broadcasts out, everyone stop. Stop communicating right this second. Halt all communication on the line. Once the line is completely clear, all devices will set a random timer, and that random timer tells them when they can begin transmitting again. I know it doesn't really seem that wonderful or that evolved. This is kind of a little bit of a legacy technology. Newer forms of Ethernet have limited this collision possibility, so it's very, very unlikely to occur. However, Ethernet is a standard that was developed in 1984. The Ethernet standard has evolved through several revisions since that point. But, again, if I'm going to teach you about a car, I'm going to start with a 1955 Chevy before I jump into a 2012 Nissan GTR. So there is the collision detection mechanism. It's basically looking for detections, broadcasts they all stop, everyone sets a random timer, and then begins transmitting again. So that's kind of a more in-depth view of the functions. Now we actually have to look at the data itself, the Ethernet frame. And just like everything else, it's gone through several renditions as well. The first one was Ethernet 2, and this was the original 1984 standard developed by Xerox and Intel and DEC, or Digital, and it was called DIX. This was developed back in the early 80s by Bob Metcalf. You can actually Google him and get his bio. And the original one had most of the standards that you'll see now. One of the things that you'll notice, though, is the addition of these extra headers here. So I'm going to go over these headers from the newest rendition, and you'll actually see as we go their purpose and function. Starting with the destination and source MAC address, real obvious what those are. Your address, where you're going, who you are. And again, same thing, 48 bits or 6 bytes. That's just identifying your physical address. So now kind of going back here to the beginning, let's look at the preamble and the start delimiter. So the preamble is an 8-byte field that is generated by your network interface card, and it contains a basic synchronization pattern of alternating zeros and ones that allows the network to easily detect this is the beginning of a new header. This is the beginning of a new frame. Again, you're having all those zeros and ones. How do you know the beginning of one header or the end of the next header? Well, the preamble and the start delimiter work in tandem to do that function. The start delimiter, or start of frame as it's sometimes called, is the last 8 bits of the preamble that marks the it's basically, what is the value again? I think it's 10101011. Don't quote me on that. I haven't memorized all this. But it basically designed to break the preamble pattern and signal the start of an actual frame where the MAC addresses are going to begin. So all this is really doing is saying, hi, this is where a frame actually exists. Then the next ones, of course, are the source and destination address. Now let's start going through this. The FCS, kind of jumping to the end, we talked about that. That is, again, the calculated value to detect if there is an error in this frame or not. Going here to the length, that actually tells you how big the header is. If you look here, the MTU, the maximum transmission unit, a packet could be anywhere from 64 to 1,518 bytes. But depending on the type of traffic, are you transmitting voice? Are you transmitting database queries? Your packets can vary quite a bit. So it works kind of in tandem with the preamble to say, this is where the frame begins, this is how big it is, so you can expect it to end here. Next on the list, DSAP, SSAP, and that basically stands for Source Service Access Point and Destination Access Point. And this is used to identify the Layer 3 protocol that is being carried by this packet. Now, as it turns out, you'll see here an evolvement here from 802.3 Ethernet to 802.3 with a snap header. This is only 1 byte, 8 bits, 256 values. We very rapidly grew beyond 256 protocols. There are actually quite a few more. So these work in tandem with the snap headers. The SNAP stands for Sub-Network Access Protocol, which was later developed to accommodate all of those additional protocols. What will happen is when you're referencing the SNAP headers, the DSAP and SSAP will be set to a specific value that says, don't look at us, look for the SNAP headers, and the SNAP header will identify the protocol. And just a little extra piece of information, TCP/IP, the protocol of the internet that we use today, is one of those designated in a SNAP header. The data, of course, like I said, that's the payload. That's the actual information that you're transmitting. What do we have left? The control. That basically is kind of basically to reduce cross-protocol broadcasts. It identifies what fields will follow and kind of works with the destination and the source service access or access point to essentially say additional fields in that layer 3 or higher protocol. Alright, so that's pretty much it. One thing I do want to point out when you're talking about the MTU, anything that is smaller than 64 bytes is typically called a runt. Anything that is larger is called a giant. When you have errors, you typically will generate a lot of runts, a lot of small packets as you have collisions and whatnot. Those are almost always the sign of a bad packet. However, it is possible to have giants and have them be legitimate. In gigabit and faster protocols, they actually have acceptable giant frames that can go beyond this to 9,000 bytes, with the convergence of having storage networks kind of share the same backplane as data networks and voice networks. To accommodate all of that extra workload, they're now allowing giant frames to run on the network. So standard Ethernet protocol was 1500 bytes, but now they've extended it with giant frames. So in the newer formats, 802.3 gigabit and 803.3 10 gig allows for the 9,000 byte frames. All right, that is really the conclusion of this video. At the request of one of my readers, I'm going to post my notes on my blog, CiscoJedi.com. So if you want to see additional notes, you can. We have a couple more videos coming up. Like I said, I think I'm going to explore some layer 2. I'm also going to probably cover some TCP/IP now. Going to go through the basics of also a computer, some processor and memory. So we have a lot of exciting videos planned. So stay tuned for more stuff. Anyway, this is the Cisco